back to the business again. So SPI, Serial Peripheral Interface, an old protocol between devices and different kind of functional devices and microcontrollers. Basically, it's between 2 points, so there's a master and there's also the slave. So there's a serial clock signal. The clock signal is always generated by the master. Then there are two data signals. One is master out, slave in, MOSI. Okay, so the direction is quite obvious here. Or MISO, master in, slave out. Actually, in order to read anything from data, you must write there something. It could be just zeros, but you need to write in order to read. So the read and write happen on the same time. The slave select signal is used to address different slaves, and okay, this is direct chip select signal, which means that actually making this a bus is very simple. You just have separate slave select signals to run for different components, different devices. One peculiar thing is that actually data rate or data content or size is not defined by the standard, so you need to read carefully the data sheet of the device what you are reading. Especially in our exercise, this SPI device is actually an A to D converter, an external A to D converter. First of all, you need to have fast enough clock speed for that A to D converter that you get good results. Then you also need to read 12 bits, and the bits are not on either of the ends. So it's basically you need to omit some of the bits, and then you don't read all the 16 bits. But I will tell you more on the exercise hints. Okay, multiple device cabling. So you have the common clock, MOSI and MISO lines, and then you have basically different slave selects for different slave devices. Simple. Okay, since there is no definition for the data synchronization, basically there are 4 different operating modes. Either leading clock edge or trailing clock edge, or and then if the clock is inverted or not inverted. Okay, so practically mode 0 and 3 are the same, and 1 and 2 are the same. But anyways, most commonly these are leading clock edge non-inverted devices what we are using. But that's something you need to check from the datasheet. And okay, in addition to the modes, it's possible to transmit either most significant bit first or least significant bit first. Okay, more considerations. But the good thing here, why this is used, 10 megabits per second easily using non-balanced lines up to 20 centimeters. So actually the speed limitation is only electrical. It's not this not this the interface which actually requires some. It's something that is only the speed limit is the physical speed limit by the ports and the lines what is driving. So this can actually go as fast as your electronics go. Okay, SPI sample. Okay, there is a how to send 1 byte from the microcontroller to a device. So first, chip select goes low, bits are clocked, okay, and this is rising edge of the clock signal, and every time when you have a rising edge you actually can read. So here at the rising edge we have 0, 0, 0, 0, 0, 1, 1, and 0. Ha. Okay. Is this 0, 0, 0 and so on this way, or the opposite? It could also be 0, 1, 1, 0, 0, 0, 0, 0. So it's either 0, let's see, that's 6 or 6, 0, depending on if this is a most significant bit first or least significant bit first. And in this case, the serial out data sent from the peripheral device, it's nothing. Okay. Okay, there's a SPI sample that 1 byte from microcontroller, 1 byte to microcontroller, same thing. So read. So basically, there's just that this depends on the device. So basically, first writing something and then reading it from this one. So this basically depends on the device totally, but anyways, that's one example. Okay, before this SPI we were talking about I2C. What is the difference? So I2C is lower. It's a low speed, long range interface. So remember, it has the standard speed is 100 kilobits per second, while the SPI easily can take that 10 megabits per second, even with the, say, few centimeter wire in between the processor and your breadboard. Okay, if you have a, for example, mobile phone, you have most probably you have both buses there. I2C for example, things that are read only once in a while and are not time critical, like SIM card interface. There you really don't need fast communication. So for SIM card, it actually uses I2C bus. Real-time clock, okay, real-time clock, yeah, you once in a while go and check the real-time clock time. And then, for example, temperature sensors. Temperature sensor is quite typical for low speed, since usually you don't need to measure the temperature at high sampling rate. On SPI, memory, audio, that kind of things, communication, devices, that kind of stuff. SPI, okay, TC74, same as we have on that I2C. It also actually have SPI interface, but on the exercise you will be using the that device with the I2C bus. Then there's an accelerator, for example, SCA3000 by, I think this is Murata SCA3000. This could be also already obsolete component. Digital barometers like that, or then 8045 series flash memory chips have SPI interface. Okay, M plus something. So, okay, wow. SD and MMC memory cards is SPI. It's SPI bus which reads the data or accesses the data on this SD card, the interface. Interfacing SD card with microcontroller is possible, and with PSoC it's actually say relatively easy, since there is a component for interfacing memory cards. Okay, communication devices like SPI, like these 2.4 gigahertz band, low range, transmitters or transceivers, NRF24 something. That's few years back. There's L01, I think it's updated versions available now. But anyways, those are pretty easy to use devices for say relatively low range applications. Particularly these actually have quite small power consumption, so you actually can run these on battery as long as you are not having those on all the time. Network interfaces, okay, I think these might be also some, let's say, maybe going away on the microcontroller world, since everything is going to wireless at this moment. So, but anyways, there are Ethernet controllers. So practically that's TCP, the SPI interface to or communicate with the device. Okay, okay, then about PSoC5 and as SPI slave. Relatively straightforward. Okay, that's just an example like that. You can actually also use SPI bus and run PSoC5 there as a slave. Just an idea for the project. The Raspberry Pi does not have A to D converter. PSoC5 does, and actually it also can be used with analog multiplexer with 8 channels. So how about making A to D converter for Raspberry Pi, which uses SPI slave interface to communication? Just an idea. Okay, PSoC5, of course, most commonly you're using that as a SPI master, quite straightforward. So there are actually these SPI MISO signal, SPI clock signal, SPI slave select signal, or if you have a these several devices, then you can actually use the slave signal and use a multiplexer to access more than one device. All right, so that's quite straightforward. Okay. More details that are important for the exercise, but not necessarily on this theory part. Okay, SPI distance extension. The SPI itself have relatively short communication distance. However, you can use line buffers. All of those lines are actually one directional, which means that you can just have a power driver there, probably a matched the lines, so not just a single line but a twisted pair line for example 90 ohm standard cabling, and then you can have matched signals, and you can actually go over 100 meters. And only limiting factor actually is the propagation delay on the line. So very fast, then you start having the clock sync and the signal coming back not in sync anymore. The writing is just fine, but the reading data from a far away device might get actually tricky. Okay, yeah, SPI summary: synchronous full duplex bus for short distance, and it's high speed. And with PSoC it's relatively easy to use it. I would say quite straightforward, with some care you need to take. Okay, so that completes this theory part of SPI bus.